Black body radiation by KayScience.com. These are two different objects. Both of them appear black. One on the left is a black object, and the one on the right is what we call a theoretical perfect black body. So this object here, which is black but is not a perfect black body, will absorb a lot of radiation, as it is a good absorber of radiation. But it will also reflect some radiation back to the surroundings. So this here is an object that is not a perfect black body. So it's a really good absorber of radiation because it's black in color, but it does reflect some radiation. So this here is a perfect black body. Perfect black body would absorb all the radiation that hits it. Perfect black body will absorb all the radiation that hits it and will not reflect any radiation that hits it or transmit any radiation. So this black object will emit radiation, and it is a really good emitter of radiation. But this here is a perfect black body. So the best absorbers of radiation are also going to be the best emitters of radiation. So perfect black bodies are not only the best absorbers of radiation, they're also the best emitters of radiation too. It's question time. Attempt these questions to check your understanding. So this graph represents the wavelength of light emitted by an object along the x-axis and the intensity of the light emitted by the object on the y-axis. So intensity is the power transferred per unit area. So the higher the intensity of the radiation, the more energy is being transferred to a given area in a certain time. So as you can see here, the radiation emitted by this object has a greater intensity than the radiation emitted by this object here. Visible light is white, but it contains a spectrum of different wavelengths that all correspond to a different color. What I'm drawing here is the visible light spectrum within the electromagnetic spectrum. So the longest wavelength within the visible spectrum is red light. Orange light has a shorter wavelength than red light. Yellow light has a shorter wavelength than red and orange light. Green wavelength of light, which is shorter. Then there's the blue wavelength of light, which has a shorter wavelength. Then there's violet and indigo, with the shortest wavelengths of light within the visible spectrum. What I'm drawing here is a filament lamp. Without a potential difference applied to the lamp will still emit infrared radiation because it has energy in its thermal energy stores, but there is no visible light that's being emitted. And when enough potential difference is supplied to this filament lamp, you'll firstly see a very dull red color, which is the filament in the lamp glowing. So if we now draw a line, which is going to show the intensity and distribution of the wavelengths emitted by the bulb at a low temperature, you'll see that the peak is here. And you'll see that there will be some red light being emitted by the filament at this temperature. And if we increase the potential difference supplied to the filament in the lamp, you'll see that the intensity of the wavelengths emitted increases because it starts to glow more. But instead of it glowing red, it's now going to glow orange. So the temperature of the filament in the lamp has increased. So now let's draw a new line that represents the distribution of the intensity of the wavelengths of light emitted and the wavelengths that are being emitted by the object. So as the temperature of an object increases, the intensity of every emitted wavelength increases. You can see that by the line. There's going to be an increased intensity of the wavelengths that are being emitted by the filament. And as we increase the temperature, the peak wavelength decreases, which now means the peak is around the orange wavelength of the visible spectrum. So now, orange light is being emitted as well as red light. So you'll now see an orange glow from the filament in the lamp. So this here is the new peak, caused by an increased temperature in the filament in the lamp. This causes the intensity of the wavelengths emitted to increase. And that's the intensity of every emitted wavelength, not just the visible light spectrum. And the peak wavelength decreases as you increase the temperature, and the peak wavelength decreases as you increase the temperature. It's question time. Attempt these questions to check your understanding. So now we're increasing the potential difference in the filament of the lamp. This is going to increase the temperature in the filament. And as you can see here, yellow light is now being emitted by the filament lamp. This is because the new peak has shifted to the left to a shorter wavelength of light, which is now yellow. So the peak wavelength decreases as you increase the temperature, and the wavelength of light at the peak is now yellow. But as you can see here, I've drawn more light rays being emitted from the filament to represent a greater intensity. So the temperature of the object increases. The intensity of every emitted wavelength also increases. Remember, the peak wavelength decreases. Remember, the peak wavelength decreases. So we've now increased the potential difference, the filament in the lamp even more, and the temperature increases in the filament. And now you see the light being emitted change color to a more white yellow light. So it's a more white color. So the temperature of the object increases. So as you can see, the new peak has shifted to a lower wavelength of light. And the intensity is also higher, which means that there's going to be more energy being transferred per unit area. So it's now emitting a white light because the filament is now emitting all color wavelengths of the visible spectrum. Because the filament is now emitting all color wavelengths of the visible spectrum, which means that it's going to be emitting a white light. As you can see here, the peak wavelength has decreased as you increase temperature. As you increase the temperature, you're increasing the intensity, but you're decreasing the peak wavelength. So at lower temperatures, you're going to have a lower intensity of the radiation being emitted by the object. And with every temperature increase, you increase the intensity of every emitted wavelength by the object. So every wavelength's intensity increases as you increase temperature. It's question time. Attempt these questions to check your understanding. Press pause to practice using those key words. The answers will follow. Press pause to go through your answers and make any corrections to your mistakes. Press pause to answer the questions. The answers will follow. And if you're stuck, just re-watch the video. Press pause to go through your answers and make any corrections to your mistakes.